Why, hello. Today we're going to go on to section 16.7 that deals with triple integrals. First of all, your book has this as their definition. If you have x, y, z, and it's part of a cube, all right, or really a rectangular solid, where x is ranging from constants a to b, y is ranging from constants c to d, and z is ranging from constants r to s, you can do your triple integral over that volume of f of x, y, z, and we could go dx, dy, dz. You also could go dy, dx. There's all different ways that you can move those around. And since x is ranging from a to b, your inner integrals are going from a to b. Y is ranging from c to d, so you have y ranging from c to d, and z ranging from r to s. Okay, so we're going to start doing triple integrals. You evaluate a triple integral just like you did a double integral. You work from the inside out. Unfortunately, you've got to do it 3 times instead of 2 times. What we're going to do today is the first few I'm going to do out longhand. It's 3 integrations, so it'll be a bit tedious watching me. Some of them I'm going to actually put them on the TI-92 and have it do it. We'll also have Maple do it, all right? And I'll comment. It's important. Setting up the integrals is what's the most important thing that we're doing today, but also many of us do have to practice because in Calculus 3, it's the hard part is when you're integrating with respect to x, realizing that y and z are constants, right? Or when you're integrating with respect to x, or when you're integrating with respect to x, y and z are constants. If you're integrating with respect to y, x and z are constants, and keeping your head straight. So this one, we don't even worry about what the region is. We just want to evaluate what that integral is. So we're going to do the inner integral first. And so we're going to be integrating. Also, notice when some of you are setting up these integrals, notice no matter how you set it up, on the outside, that last limit of integrations, they have to be constants. If you have variables there, you're not going to be getting a number. You're going to be coming and seeing me and saying, why am I getting an x or a y or a z in my answer? All right, so in this one, we're doing the inner integral 2x, y, z, dz, as z ranges from 0 to y. Okay, and in this one, first of all, we look at it, because we're doing the integral first, and we look at that one and we say, okay, since we're integrating with respect to z, x and y are constants, so I bring them along for the ride. So in reality, I'm just integrating 2z dz, which is z squared. And if I take the partial of this with respect to z, indeed I would get 2xyz, which I have inside. And notice this is as z ranges from 0 to z ranges from y. And especially when it's a triple integral, you want to write, I'm integrating with respect to z, z's ranging from 0 to z's ranging from y. So I'm plugging in for z, y, so I get xy times y squared minus xy times 0 squared, and I get xy cubed for my inner integral. Now, unfortunately, since it's a triple integral, we're going to have to do this 3 times. So I take my xy cubed, and now I'm integrating from x to 2x with respect to y. We're doing x to 2x with respect to y. Again, x is a constant, so it comes along for the ride. I'm really just integrating y cubed dy, which gives me y to the 4th over 4. And we're integrating as y goes from x to y goes to 2x. So I have x over 4 times y to the 4th, so I put in the 2x, and that's going to the 4th, minus x over 4 times, and x is going in for y. So this gives me what? 2 to the 4th is 2 times 2 is 4 times 2 is 8 times 2 is 16. So I have x over the 4th, x over 4 times 16x to the 4th, minus 1/4 x to the 4th, and, x times x to the 4th is x to the 5th. So I have 16x to the 5th over 4, minus 1x to the 5th over 4, which I guess I'll write as 15x to the 5th over 4. And that's my second integral, because 16 minus 1 is 15. Okay? We all okay? All right. Now I take that, and now I'm integrating 15 over 4 x to the 5th dx as x is ranging from 0 to 1. And let's see, that gives me 15/4. Increase your exponent by 1, divide by the exponent. So we have 15 over 24 x to the 6th as x goes from 0 to 1. And that's going to give me 15/24 times, put in a 1, minus put in a 0, gives me 15/24, and let's see, 3 goes into the top, 3 goes into the bottom, and my final answer is 5/8. Okay, so it's nothing new. I mean, if you didn't come to class today, I think you would have been able to figure out how to do that. Okay? You've got to keep your head straight, though. And you want to, you know, each time there's all kinds of places to. Don't squish it all into one little, one little section of a sheet of paper. Give yourself plenty of room to spread it out. And also, I strongly urge, like when you're doing that inner integral, write what variable you're plugging in for, because I mean, you've got an x, a y, and a z there. You can go pretty wacko. Let's do this one. I chose this one because it's an e to the u, which I think all of us benefit from reviewing how to integrate exponential functions. So the inner integral that we're doing is from 0 to y of z e to the minus y squared dx. We're integrating with respect to x. So in reality, we can factor out z e to the minus y squared, and we just have a 1 dx inside. Because they're constants. We're integrating with respect to x. That's all in terms of y's and z's. So you could factor that out if you wanted to. And so the integral of 1 dx is just x, and we're ranging from x is 0 to x is y. So I can bring my constant out here, and for x we're plugging in y, minus for x we're plugging in 0. So we have here yz e to the minus y squared. Now I take that, and that's going to go into my second integral. Okay, and my second integral is from 0 to z, and we have yz e to the minus y squared dy. That's my second one, dy. Again, anything, as long as you have a product, anything that doesn't have y in it, you can drop kick him out front because it's a constant. So I'm going to put that z out front because that's a constant when we're integrating with respect to y. And I say, how do I do this integral? This is e to the minus y squared times y dy. I think this is going to be an e to the u du. So what are we going to let u be? We're going to get u be the exponent minus y squared. So du is minus 2y dy. So what am I going to put in for y dy? Well, if I multiply by minus a half on both sides, minus 1/2 du is going to equal y dy. So for this integral, I bring z along for the ride. I'm going from 0 to z. This is y goes from 0 to z, of course. Minus y squared is u. And for y dy, I'm going to put in minus 1/2 du. And definitely the integral of e to the u du is e to the u. I can't be plugging in 0 and z yet because that's for y. So I say, okay, I have minus 1/2 z. E to the u is e to the minus y squared, and we're going as y goes from 0 to y goes to z. Now keep your head straight. A lot of times when people are plugging in 0, they say, oh, it's just 0, because that happens a lot, but it doesn't in this case, because this is equal to minus 1/2 z times, now we're putting z in for y, so we'll have e to the minus z squared, minus, putting in a 0, e to the 0. But you guys tell me, what is e to the 0? 1. Very good. So I have minus 1/2 z times e to the minus z squared minus 1, which might be helpful if I multiply this out. So I have minus 1/2 z e to the minus z squared plus 1/2 z. If I just multiply it out. Okay. Everybody okay? Now, unfortunately, I've got to take this and do the last integration. So now I'm going to go the integral from 0 to 1 of minus 1/2 z e to the minus z squared plus 1/2 z dz. And as you can see, I can consume the entire lecture today just doing a couple of them. So we're not going to go too wacko. You know, we're going to do a few of them, but not too many. All right, now I'm going to break this up. Let's do this integration first. Minus 1/2 integral from 0 to 1 of z e to the minus z squared dz plus 1/2 integral from 0 to 1 of z dz. You know, because I took this integral plus this integral. When I took this integral, I just factored out the minus 1/2. When I had this integral, I just put the 1/2, because we're using the integral of f plus g is the same as the integral of f plus the integral of g. I think we're going to do this. We just did this one 2 minutes ago, but let's just do it again. I have the integral from 0 to 1 of z e to the minus z squared dz. We just did it 2 minutes ago, but let's do it again. How are we going to do it? U substitution. U is minus z squared, so du is minus 2z dz. So if I multiply through by minus 1/2, minus 1/2 du is z dz. So this becomes the integral from 0 to 1. E to the minus z squared becomes e to the u, and z dz gets replaced with minus 1/2 du. And so therefore this is equal to minus 1/2 e to the u, which is minus 1/2 e to the minus z squared, as z ranges from 0, z ranges from 1. A lot of times students will start plugging in the 0 and the 1 here, but no. Question?
Are you forgetting the 1/2?
Out here?
Yeah.
What I'm gonna do is I'm gonna go minus 1/2 and then plug in what we figured out that integral to be. Okay? So plugging this in, I have minus 1/2 times, putting in a 1, I get e to the minus 1, minus, putting in 0, e to the 0 is 1. Okay? Now notice that was just the integral from 0 to 1 of z e to the minus z squared. I got this. So right here, here's the integral. This minus 1/2 has to come along for the ride, but this integral right here, I just figured out was minus 1/2 times e to the minus 1 minus 1. Now I have to figure out what this is. Well, this one's a pretty easy one to do. I think I'll do that right here. I have 1/2 integral of 0 to 1 of z dz. So that's 1/2 z squared from 0 to 1. 1/2 times 1/2 is 1/4. Plug in a 1, I get 1. Plug in 0, I get 0. So it looks like I have equals 1/4. So this integral is plus 1/4. So let's see what we have here. We have minus a minus is a plus. So I have 1/4 e to the minus 1 minus 1 plus 1/4, which equals 1/4 e to the minus 1 minus 1/4 plus 1/4. They cancel each other. So this is my final answer. And your book likes to do this. They say e to the minus 1 is 1 over e. So I could write the answer as 1 over 4e. Okay? You need to practice, but you don't need to do a million of them. You need to do 5 or 6. Okay. It's also a good idea, and I'll show you in a minute, how you can use Maple to check yourself as you go. All right, or the TI-92, or an 89. Now, the remainder of the period, we aren't going to be so lucky that they're going to hand us the integrals. We're going to have to set the integrals up. So a good part of what we're going to be doing today is how do you set up the integrals. We're integrating over the solid, which we're calling e, of the integral z dv, where e is the solid tetrahedron bounded by the 4 planes, x equals 0, y equals 0, z equals 0. Now I hope we all realize x equals 0. If x is 0, you're in the yz plane is what you are. If y is 0, you're in the xz plane. If z is 0, you're the xy plane. So we're just having the 4 planes that you get with your axes. So drawing my region, x equals 0 gives me remember this is the x plane. I mean this is the x-axis, the y-axis, the z-axis. So if x is 0, we're right here. We have the yz plane. And in fact, it goes forever, but if I draw it forever, it's just going to be hard to see my picture. If y is 0, we're in the xz plane, right here. So that's one of my walls. And if z is 0, you've got the floor here. Okay, so I've got those 3 sides. In addition, I have the plane x plus y plus z equals 1. How do I draw that plane? Well, let's see. If I let y and z be 0, in other words, if I'm on the x-axis, x is 1. That's the point 1, 0, 0. If I let x and z be 0, you get y be 1. So that's the point 0, 1, 0. And if I let x and y be 0, z is 1. So that's going to be the point 0, 0, 1. So if those 3 points are on the plane, I can play connect the dots. Can you see my tetrahedron? Can you see my tetrahedron? It has, this is its roof, and we could consider this to be its base. And then you have this for the side and that for the other side. It has, the reason I call it tetrahedron, it has 4 sides, 1, 2, 3, and then this slanted side. Now, how do we set up a triple integral? All right, now remember, when you did double integrals, I said, remember, like if I did a double integral and I had a region that looked like this, let's say. Okay, maybe it looked like this, and maybe this is like, let's pretend this is y equals 2x, and let's this point be maybe 1, 2. So this is the line y equals 2. And suppose I'm integrating over that region. If I decided to integrate with respect to x first, remember what I did. I said pick an arbitrary y. Pick an arbitrary y in your region, and then say what is x ranging from. You didn't do it on the x-axis. You picked an arbitrary point in the region and said, what is x ranging from? And then here I would go, x is ranging from 0. Aha, Mrs. Strocko wrote this as y equals 2x. So I'd have to solve for x. And I'd say, oh, x is ranging from 0 to y over 2. And then if I summed all those up, right, what is my y ranging from? Your y is ranging from your lower bound 0 to your upper bound of 1. But the point is, 2, thank you very much, 0 to 2, because it says y ranges from. Now the point is this though, when I integrate it with respect to x first, I picked an arbitrary y, you with me, and then look to see what x is ranging from. Now with this one, when you have a triple integral, 9 times out of 10, our base is going to be in the xy plane. We're going to do some at the end of the period today where that's not going to happen. We're going to have to pick our base to be in the yz or in the xz. But we're going to start out with it being in the xy plane. Your base has to be a point that, if this is my base, if I pick any point in the base, all right, now since that's in the xy plane, I'm going to move in the z direction. And I've got to figure out my lowest z to my highest z from in that solid. You with me? In that 3-dimensional solid. So in this one, it's quite obvious. If I'm on this base, the lowest z is z equals 0, and the highest z is going to be the rooftop, right? And the rooftop is the plane, x plus y plus z equals 1. But if I say, oh, if I'm on the rooftop, on that slanted plane, what does z equal? What's quite obvious, z is equal to 1 minus x minus y. I have to solve for z, just like before we had to solve for x or solve for y. So in setting up this integral, my base is in the xy plane, so guess what? Since the base is in the xy plane, my dx, dy is done last, and dz is done first. This was your base. My base is in the xy plane, so that's done last. Now I could go dx dy, or I could do y dx. I don't really care. We'll figure that out in a minute. But you've got to pick an arbitrary point in your base and see how the other variable is changing. Well, how is my other variable changing? You just told me. If I take an arbitrary point on the base, my z is ranging from z equals 0 to being a point on the plane, which is z equals 1 minus x minus y. Now I'm going to be integrating with respect to x and with respect to y. To do that, I strongly urge you to redraw your base just using the x and the y-axis. Some students can picture this beautifully, the xy plane in 3-dimensional space. Other students die. So I'm going to redraw this picture just in the x, y plane. Now notice, if I'm in the x, y plane, forget about the z's because they're zeros, right? So this one point is 1, 0. That's right here. And this other point is 0, 1. You with me? And this line in the xy plane is just going to look like this line here. And how are we shading it? Well, you're shading it from the line to the origin. So the region looks like that. Are you all with me? Now, my last part of my triple integral is integrating over that region. Okay, now you guys tell me, do you want to go with respect to x first and then with respect to y, or vice versa? Which way you want to go? Okay, I have dx dy, that's fine. We can do dx dy, or we can do dy dx, whatever you prefer. If I go with respect to x and then with respect to y, how would you have your x's range? Okay, now, if x is ranging, we have to pick an arbitrary y. We got to go this way, right? So it's quite obvious I'm starting out with x equals 0. What am I ending up with? What's this line here? This is the line y equals x. So if I'm integrating with respect to x, x equals y. Oh, you're right. It's not y equals x, because what's my slope? Down 1, back 1, right? So my slope is minus x. And then if I'm using y equals mx plus b, my y-intercept's 1, so it's minus x plus 1. And just check me, make sure that works. If I put a 0 in for x, I get y to be 1, which that point's correct. If I put a 1 in for x, minus 1 plus 1 is 0, so it works. So we're going to be integrating from x equals 0 to this line, but I've got to take this line and solve for x. So if I add x on this side, I get x equals and subtract y. It'll be x equals 1 minus y. Are we all okay? Because if I take an arbitrary point in the region, what is x ranging from? From 0 to x, integrating with respect to x, which is 1 minus y. Again, if you want to check, here y is 1, 1 minus 1, x is 0. Here y is 0, 1 minus 0 gives me 1. It works. And then if we sum all those up, what's my y ranging from? From 0 to 1. This integral is not going to be any rocket science one. It's going to be one in which you're going to get polynomial after polynomial after polynomial. So this is a good candidate. Why don't I practice doing this on Maple for a change? Okay, to show you how to integrate on Maple. Reminding you how to integrate on Maple, let me just do a simple integration first before we put that big guy up. If I just wanted to do the integral of x squared dx as x ranges from 2 to 5, the Maple command is just int, parentheses, what your integrand is, x squared, okay, comma, x equals 2 dot dot 5, and every output command has to end in a semicolon. Okay, so let's put this on Maple and see what we get. Okay, we'll pop that there. You all have that copied down. Okay, turning on Maple. Okay, there you go. To do my integral, that's this one right here. Okay, I'm going to go now I want to show you another thing I can do. If I type capital INT, I'm going to go z as z ranges from 0 dot dot 1 subtract x subtract y parentheses semicolon. And let me show you with the capital INT, it does not do it. It just does it in pretty print. If you're a novice at Maple, that's a nice thing to do, because then you can see, oh yeah, I copied it just right. Go back up, click on it, backspace the capital I, make it a lowercase I, and it will do the inner integral. This is wonderful for you to do, like if you're in the math lab and you do that first integration, you do it with paper and pencil and then check to see if indeed you have the right answer there. By the way, though, they have this in factored form. You might not, you might have it multiplied out, so you'll have to check to see. Now, I'm doing the next integral is going to be the integral from 0 to 1 minus y of what we just got, which was 1/2 1 minus x minus y squared dx. Okay, now the beauty of this is I'm going to go int, parentheses. I'm going to use semicolon. The percent key. The percent key in Maple means bring down the last. Now it's not previous entry. It's the last thing that's been entered in the computer. If you're hopping around your Maple worksheet, you can just create havoc with that percent. But that just means previous entry. All right? I want to integrate my previous entry as x equals, and I'm going from 0 to 1 minus y. Close parentheses for the integrate command, semicolon. Hit enter. Okay? Lastly, I want to take that and integrate 0 from y. I'm going to go ditto dy. And so I'm going to go int parentheses semicolon as y goes from 0 to 1. Close parentheses, percent key, and they got 1 over 24, which is the correct answer. Okay? If I'm working for an engineering firm and I actually need to use multiple integrals to evaluate something, I'm not going to do it by hand. I'm going to use Maple, or I might use a 92 or an 89. So it's important to practice those skills also. Okay, let's look at the next problem. Same problem, if you ask me. It's no different. It says evaluate the triple integral y dv, where E is the solid, bounded by the planes x equals 0, y equals 0, z equals 0, and the plane 2x plus 2y plus z equals 4. Again, if you look at this particular one, if you look at what you have here, x equals 0, it's important for you to realize when x is 0, you're on the yz plane. Now granted, I'm just drawing the first part in the first octant. You can go all the way back, you can go in the negative direction, backwards and downward. Y equals 0, if y is equal to 0 here, you're in the xz plane. And if z equals 0, you have the floor of the xy plane. And the 2x plus 2y plus z equals 4 is a plane. They usually pick it so that it'll be one that's laying in the first octant, so your drawing won't be okay. Notice if I let y and z be 0, what does x equal? 2. So this is the point 2, 0, 0. If I let x and z be 0, y is 2. So this is the point 0, 2, 0. And if I let x and y be 0, z is 4. 1, 2, 3, 4. So that's the point 0, 0, 4. If you can make your base be the xy plane, do it. So there's my base. And notice, if I'm standing on that base, if I go up in the z direction, down in the z direction, I don't have to go down in the z direction because I'm already on the floor. Always, 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 I'm going from z equals 0 to z equals the plane. So we're going to integrate with respect to z first. You figure out where your base is, and that, since that's in the xy plane, dx dy is going to be last. It also will be helpful, let's draw our base right here. Maybe I'll get my equations a little bit better this time. This is the point 2, 0. This is the point 0, 2. This is the line that connects them, and the region, that base, looks like this in the xy plane. All right, and let's see, this equation right here, you're going down 2, back 2, that's a slope of -1, so it's y equals minus x, and it's plus b, my y-intercept's 2. So it's going to be y equals minus x plus 2, just checking. Plugging a 0 in for x, yeah, I get y equals 2. Plugging a 2 in for x, -2 plus 2 is 0, it works. All right, now, since the base is in the xy plane, notice the function we're integrating is y. It's y dv, okay? But since the base, I take an arbitrary point in the base, I go perpendicular to the base. What is z ranging from? Z is ranging from 0 until I get up to the plane. So it's going from 0 to up here. What is z? Z equals 4 minus 2x minus 2y. Okay. Now, we have to integrate over the base. I find this picture a little bit more helpful. Do you want to go dx dy or dy dx? Dx dy or dy dx? Let's do dy dx. We did dx dy last time. Since we're going dy dx, we have to pick an arbitrary x and ask what is y ranging from. Taking an arbitrary x in that region, y is ranging from 0 to minus x plus 2. Which maybe I'll write as 2 minus x. It's a little nicer to write that way. And if we sum all those up, x is ranging from 0 to 2. Again, this is one that it'll be a bit tedious to do with paper and pencil, but they're polynomials. It's a matter of, x squareds and that type of stuff. So why don't we put this on a TI-92 to see what our answer is. Okay, so I'm going to pop this on, turn on my calculator. A TA89 also does the same thing, and in fact the keystrokes are pretty much the same. I'm going to do my inner integral first. In fact, I can move this away and then you won't even get, in fact, I'll put this over here and you won't even have to see it. My inner integral is going to be, I'm going to go shift and then hit my integral sign. My function is y, comma, as y. Now you keep your head straight with the TIs. You go comma. With maple, you go equals. All right. So I went. Whoops! I didn't put my integral sign. Clear. Let's do integral again. Integral. There you go. Of y as y. Oh, Mrs. Strocko forgot her dz here. Okay. Right, because we were integrating as z ranged from 0 to 4 minus 2x minus y, and then y went from 0 to 2 minus x, and x went. So this is the integral I'm going to be doing first. Okay, so coming back here to the calculator. All right, so he knows I need to turn it on. I'm going to go, I'm integrating y as backspace z. Goes from 0 to 4 minus 2 times x minus 2 times y. Notice with these computer algebra systems, I prefer always to put in, sometimes with the TIs, I type something wrong. Y as z ranges from, no equals, that's in maple. It's commas, right, z comma. As z ranges from 0, comma, 4 minus 2x minus y, and hit enter. And you can see on the left-hand side, you can see right here on the left-hand side, that's the integral that I did type it correctly, and this is the answer that I get. So now we're going to do the outside, the middle one. This one. All right, and so on the TI-92, what I can do, I'll bring it back, because we're not done, we got to do 3 of them. I'm going to go integrate, all right. I just want to move that away because I always get that awful shadow. Notice, with this calculator, if I push the arrow up, I can highlight that, and then hit enter and just pull that down. And then I go comma as my second integral y, comma, ranges from, and we're going 0 to 2 minus x, 0, comma, 2 subtract x, close parentheses. So I have my integral as y, comma, goes from 0 to 2 minus x. Hit enter. That's my second integral. Then to do the third one, I've got to go integrate. I take my arrow just to highlight that, hit enter, it pulls it down, comma, as x goes from 0 to 2, close percent, enter, and I get 4/3. Okay? I do think those tools are very, very helpful just because there's so many places that you can get bogged up and it's hard to find your mistake. Okay, let's look at this one. The integral of xz dv, where E is the solid tetrahedron with vertices 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. Let's just draw our region first. They're telling me I have 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. Again, I've done 3 of these, so you can realize this one, why not? Let's make the base be right here. The only problem is we have to come up with the equation of the plane. Now you might not remember this, or you might remember this. Just a little review from chapter 13. If you have a plane that's crossing the x-axis at A, 0, 0, the y-axis at 0, B, 0, and the z-axis at 0, 0, C, a quick and dirty way to get the equation for your plane is as follows. Do you remember how to do this? X over A plus y over B plus z over C equals 1. Notice, this is definitely a plane because it's a constant times x plus a constant times y plus a constant times z equals a constant. So that's the equation of a plane. Notice if you put in A, 0, 0, you get 1. If you put in 0, B, 0, you get 1. And if you put in 0, 0, C, you get 1. This is a very nice way to get an equation of that plane. Very helpful. You know, we could do the thing with the vectors and take the cross product, but if I can do it this way, I think I will. Okay? So what is the equation of this plane? It's going to be x over 1 plus y over 2 plus z over 3 equals 1. Or z over 3 equals 1 minus x minus y over 2. And usually we're going to say, what is z ranging from? So I think I'll multiply through by 3, and I'll get 3 minus 3x minus 3 halves y. Okay, everybody okay with that? So that's what my z is. Now before I set up my integral, I'd like to draw my base. And I ran out of space here, so I think I'll do it. Okay, and what does my base look like? Let's just get points that are on the base. We have the origin, we have 1, 0, 0, and we have 0, 2, 0, and it looks like this. That base looks like this. And we have to get this equation. Well, what's the slope of that line? I'm going down 2 over 1 minus 2. Plus b, b is 2. Okay, and just double checking, if I put a 0 in for x, yeah, I get 2. Put a 1 in for x, I get 0. Now we're ready to do our integration. It's xz. You take a point in your base. Here's my base. What is z ranging from? Z is ranging from 0. Notice this is dz. I forgot to put that last time. Z is ranging from 0 to that plane. The equation of that plane was 3 minus 3x minus 3 halves y. Because if I take an arbitrary point, I'm going from 0 to that oblique plane, which we have right here. Then all we have to do is integrate with respect to the base. I think it's much easier to have the base. I mean, if you're okay with using this and saying, you know, what my y is ranging from here to here, what's the equation, that's fine. But I like drawing it here. Why don't we, since I have y equals, let's integrate with respect to y and then with respect to x. So what's my y in the base ranging from? From 0 to 2 minus 2x. And then if I sum all those up, my x's are going from 0 to 1. Again, it's very tedious. I mean, if you do this out with paper and pencil, you'll see that it's not a pleasant sight. You got to write neatly and keep your head straight. But if you go through and do it, the answer you're going to get is 27/8. I want to spend my time today building these integrals. Okay? Pardon? Oh no, it's not. 3/20. The next one's going to be 27. 3 over 20. Okay, but I think drawing the pictures, setting up the integrations is what we're going to spend time to do, even though you guys do have to practice with the integration. Okay, now let's look at this one. This one, we might actually do this integration out for this guy. And this one, E is bounded by the cylinder y squared plus z squared equals 9, and the planes x equals 0, y equals 3x, and z equals 0, all in the first octant. Now before I put everything all together, we'll put it all together in a second, do you know what y equals 3x looks like? Now we're in three-dimensional space here, guys. Normally y equals 3x is a line that looks like that, right? But if we're in three-dimensional space, you're going to have this line coming down like this, right? You with me? That's y equals 3x in three-dimensional space. But wait a minute. Since I don't have a z, remember what you do? You take your graph and you drag it along the z-axis. It's a plane. It's a plane that's perpendicular to the xy plane. Think about why that's true, because look here. This point right here might be, since it's y equals 3x, if x is 1, y is 3, and z is 0. But notice, a point up here, 1, 3, 5, is also going to satisfy that equation because there's no place to put 5, right? So that's a plane. It's a plane perpendicular to the xy plane that in in the xy plane you have y equals 3x, but you're going perpendicular to it. Okay? So it's like you're cutting it off. You're cutting it off. Okay, now let's try to draw this picture, because that's the hardest part. Well, first of all, I'm going to do x equals 0 and z equals 0. Okay? X equals 0 is back here. Right? Right? That's back there. How about z equals 0? That's the xy plane. That's right here. So we're using, this is our floor. Now also they say that I'm in the first octant, so that's good. All right, we're just in the first octant. Remember, the first octant is where x, y, and z are all positive. Now you guys tell me, what does y squared plus z squared equals 9 look like? It's a cylinder. In the YZ plane, it's a circle, and then we drag it along the x-axis because there's no x. Now, they only are worried about the part that's in the first octant. So I'm not going to draw the whole circle. I'm going to draw the part that's in the first octant. Notice it does come back here like this, and it does go way down here, but since we're only worried about the first octant, why mess up our picture? Now I like to take my picture here and redraw it, and then I like to drag it. Okay, you see, sort of like when those sunroofs people are putting on their backs. Okay, you see what's sort of, can you see it? Well, not too bad picture. By the way, what's this point right here?
0, 3, 0.
Aha, y is equal to 3, right? That's the point 0, 3, 0. What's this point right here? 0, 0, 3. And how can I describe that surface? Well, if y squared plus z squared equals 9, z squared is 9 minus y squared, or since z is just, we're taking the positive part. Okay? That's what that surface is here. Now, so far, I'm doing okay. I've got x equals 0 was the yz plane. Z equals 0 was the yz plane. And then I have the line y equals 3x. Y equals 3x is coming out like this. And what you're doing is you're taking your knife and you're slicing it. You with me? You're slicing it. Now notice, when I come down and slice it, this point's part of the slice because we're slicing it, this part, and look here. Can you see? Here's your roof. You see my roof? Do you see where my base is? Where's my base? Down here. This is my base. And here's the rooftop. Notice, if I take any arbitrary point in the base, and I go perpendicular up, I end up with, on that curve, that curved surface there. Okay? So, I think before I do anything, I better be able to draw my base. Okay? So to draw my base, I'm looking here and I'm saying, okay, you have the line y equals 3x as part of it. You have the point right here, which is 0, 3, 0. Well, 0, 3 goes this way. Right? 0, 3, 0. And then that line goes like here. And then we have the origin. So I can see my region. You see how I did that? Notice this line right here is y equals 3 right there. This line right here is y equals 3. But you notice what I did is I drew my line. I know what y equals 3x looks like. I said, what's that point? You guys help me. Tell me it's 0, 3. I plot 0, 3. I plot 0, 0. And I can see this region is hugging the y-axis. So it's hugging the y-axis right here. Okay, now let's set up our integration. I don't need this just yet. What am I going to integrate with respect to first? I'm integrating z, and you told me with respect to z. So I take an arbitrary point in my base. What is z ranging from? 0 to, okay. Then, here's my region. All right. How do you want to integrate? dy dx or dx dy? Don't care. Since I got y equals 3x, why don't we go dy dx? It doesn't matter. Now notice sometimes though, if this integration is a little uncomfortable, you might try switching them and it might be a little bit easier. Okay, that does happen. Well, let's see. I'm going to go dy dx. So what is y ranging from? Take an arbitrary x. What's my y ranging from? 3x to 3. And then if I sum all those up, oh, I didn't say what this point was. Well, if this point is y is 3, it's quite obvious that x is 1, right? Because 3 times 1. So x is ranging from 0 to 1. Okay. All right. You know, this one, I'm not going to do. What happens is, well, yeah, I'm not going to do it. You get 27/8. What happens is, God is good in this one. When you do this integral, you're going to get 1/2 z squared. When you plug in z equals square root of 9 minus y squared, you square root, you just get what's inside. So this next integral just is in terms of y, and it's a nice little polynomial. And then, you know, so it's just a plug and chug kind of thing. Pictures are what's important. Okay, look at this one. I like this one. Put a star by this one. Okay. Evaluate. The integral over solid E of square root of x squared plus z squared dv, where E is bounded by the paraboloid y equals x squared plus z squared and the plane y equals 4. Okay? This one will go all the way to the end. Bringing this down, I want to draw what my solid looks like. First, I have to draw y equals x squared plus z squared. What axis is this paraboloid going to be hugging? The y-axis. Right? Now we're coming down and we're slicing it with the plane y equals 4. 1, 2, 3, 4. Y equals 4 comes down and is looking like this. So when I slice that, I'm getting, oh, my picture's awful. Ignore that part. All right, I'm slicing it at y equals 4. This is your paraboloid right here, which is y equals x squared plus z squared, and then we're slicing it. In fact, let me draw the picture one more time to make it a little bit prettier. You have your paraboloid, and when I slice it, that face is what I get for y equal to 4. And right here is the paraboloid y equals x squared plus z squared. Can we all see what I got there? Because you got this lovely paraboloid, but then you cut it off. And we're integrating with respect to this solid. Where's my base? I need a base. So that is, if I move in the other direction, that coordinate, I can tell you exactly what it's ranging from. This cries out to make this be my base. Now notice that base right there, since y equals 4, this part that I'm getting, that I'm cutting it off, is the part that has x squared plus z squared equal to 4, with y equal to 4. You see what I did? Because if y is 4 and I'm on the paraboloid, if y is 4, x squared plus z squared is 4. So I put a 4 in for y. Now if I make that be my base, notice if I take an arbitrary point on that base, all right, arbitrary point in that base is in the xz direction, you with me? I'm going to move in the y direction, and I can see what my y is ranging from a point on the surface to a point on the base. I'm going to integrate with respect to y first. And then we can do the dx dz stuff. Now let me ask you, what is y ranging from? We always want to go from lower value to upper value. Well, when I go in the y direction, when I'm on the paraboloid, y is x squared plus z squared. And when I move in increasing y, when I'm on the base, y is equal to 4. Do we all see that? If I make this be my base, since this base has xz's in its equation, it's parallel to the xz plane, we have to take a point in the base and say, what does y range from? My lower value, because notice increasing y goes this way, so my lowest value is on the paraboloid, and my highest value is on the plane y equals 4. Before I do my dx dz's, let's draw the base. What is the base?
XZ.
Well, yeah, but what does it look like?
Circle.
It's a circle. Notice we have y equal to 4, but the equation is x squared plus z squared is 4. Because remember, this was cut off by y equals 4, and I took 4 in here on the paraboloid and got x squared plus z. That's an equation of radius 2. And this is my base. When you have a circular region, what do you integrate with respect to? What kind of coordinates should you use? Polar. So what I'm going to do is, I'm not going to do this as x squared. I'm going to do this. I'm going to go integrate square root of x squared plus z squared dy. And again, this is going from x squared plus z squared to 4. But when I do the base, I'm going to go r d theta, because look here, what's r ranging from? 0 to 2. And what do all your spokes have to go from? 0 to 2 pi. Now the only thing you have to keep your head straight here is, before we always said x was r cosine theta, y was r sine theta. In this case, z is taking the place of y. So x is r cosine theta, y is r sine theta, excuse me, z is r sine theta, and x squared plus z squared is r squared. So look at this wonderful integral. This isn't too bad, guys. Look here. If x squared plus z squared is r squared, this inner integral is going x squared plus z squared is r squared. I have the square root of r squared, which is r. X squared plus z squared is r squared. And look at this integral. I'm not going to finish this. You guys can. Look how easy that is. An integral of r squared dy is just going to be r squared y. You're going to be plugging in, you know what I mean? It's easy. It's easy. You guys can finish it. And if you do, you'll get a wonderful 128 pi over 15. It's not hard. Yes?
Can you use that one step, the dy and r squared?
Sure. You're going to go, we're doing the integral from r squared to 4 of r squared dy. Since we're integrating with respect to y, r squared is a constant, so I can factor out the r squared. So the integral of 1 dy is y. And we're going from y is r squared to y is 4. So we take our r squared constant out. We're putting a 4 in for y, minus we're putting an r squared in for y. And that will give us 4r squared minus r to the 4th. I might as well finish it if I went this far, okay? Now I take my 4r squared minus r to the 4th, and my middle integral was just going from 0 to 2 dr. So, I mean, this is easy. I'm going to get a 4/3 r cubed minus 1/5 r to the 5th. and we're going from 0 to 2. You're going to plug in a 2 and you're going to get 8. 32 thirds minus 243 fifths, but I've already done it before, and we end up with 64 fifteenths. I don't feel like taking the time to put it on the calculator, but you're just putting in 2 minus putting in 0. And now we do our outer integral, which just goes from 0 to 2 pi of 64 fifteenths d theta. This is dot, 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 because you have to do a little bit of work there. And this is going to equal 64 fifteenths theta, as theta goes from 0 to 2 pi, which is 64 fifteenths times 2 pi minus 0, which gives me 128 pi over 15. Very nice problem. So sometimes you got to think outside the box. What I did here, the thing to remember is when I looked at my base, and I redrew it in the xz plane. Notice this is the xz plane, but it has y equal to 4. But that cross section is a circle. And when you have a circular region, it cries out to use polars. And sometimes I have to think, oh, it's polars, but we're always thinking about x's and y's. No, I can do it with x's and z's instead. It's the same thing. Okay, 2 more things I want to do. One thing I want to comment on, and then 2 things I want to do. Notice, just like when we did double integrals, and if we said if we make that integrand be a 1, a double integral gave you the area of the region. With a triple integral, if you let that integrand be 1, that's going to give you the volume of your solid. And the reason is because these triple integrals mean sum, sum, sum. Well, if you're summing up all your delta v's, you broke it all up in a bunch of little pieces and you added them up all up. If you add up all your delta v's, what are you getting? You're getting volume. Okay, so the point is, if I have a triple integral and the integrand is 1, it gives me the volume of that solid. And I prefer, to tell you the truth, to figure out volumes of solids, I much prefer using triple integrals than to be using the doubles like you did for your homework. Okay, if I took the test, I wouldn't use double integrals to find the volume. I find it much easier, and let me show you why. Let's just set these 2 up before we call it quits today. Use a triple integral to find the volume of the solid bounded by the cylinder y equals x squared and the planes z equals 0, z equals 4, and y equals 9. Now, the hardest part probably for you guys is drawing the picture. Z equals 0, where's that? XY plane. I want you to always zero on that first. Okay, now y equals 9 is going to be something coming down here like y equals 9, right? What does y equal x squared look like? It's a cylinder, okay? It's a parabola in the xy plane. So you come back here. Since it's y equals x squared, it's straddling the positive y-axis. And then it comes around here. Now that's I'm in the xy plane here. But since I do not have a z in the equation, what do I do with that sucker? I drag him up. Wish I had more room to drag him. I always like to draw my axes again. Parallel. That'll work. I drag him up. It comes down like this. Okay, can you picture it? Okay, now, z equals 4. What's z equals 4? It's a plane parallel to the xy plane. Why don't I make this be z equals 4 right here? Right, because it's cutting it off. Are you with me? He's cutting them off. And what's y equals 9? Well, y equals 9, I come down here. I don't like my picture totally. Let me draw it again. Mrs. Strocko. The 1 comes down like this. Okay, let's have him extend it a little bit, because this is going to be y equals 9 right here. Okay, and if I bring that down along here, I need it parallel to that. And we'll have this one go. and this up here. Now notice, do you see this base right here? This face right here is what you get when you come down and you slice it at y equals 9. That's your y equals 9 right there. This cylinder right here is your y equals x squared, and this face up here is your z equals 4. Okay? Now, to find that volume, we have to decide, where do you want to make your base? If you can get by with the xy plane, that's what you want, right? Do you see this base is just beautiful right here? Isn't that a lovely base? Notice this face right here gets cut right, like right there. Okay, so we're going to go integrate 1 dz. Now what's z ranging from? Take an arbitrary point in the base and go perpendicular to the xy plane. You're going from 0 until you get to 4, right? To the top, the part that was cut off. We're going from z equals 0 to this part that got cut off, z equals 4. Now I much prefer to draw my base in the xy plane. Now I know what this curve right here is. It's y equals x squared. And what's this? That's y equals 9. So if this is y equals x squared, this is y equals 9. What are these little corner points? What's that point right there going to be? Well, y's 9, so it'll be 3, 9. And that'll be negative 3, 9. Okay? Now we got to decide. We can integrate with respect to x, with respect to y. Which way you want to go? I think I'll integrate with respect to y, and then with respect to x. Take an arbitrary x. What is y ranging from? X squared to 9. And then if you sum all those up, your x's are ranging from negative 3 to 3. Okay? Everybody okay? Again, if we did this, which we're not, we'll get 144. I mean, I could have had this lecture be 3 hours, I think, if I did all the integrations. Okay? One more. Say it again?
Why you took the equation as just 1?
Why did I take? Because, very important, when you're integrating over a volume, if you let that integram be 1, notice what you're doing is you're summing up all your delta v's. And so if you're summing up all the delta v's, what you're going to get is the total volume of that solid. And you see in this particular one, they said use a triple integral to find the volume of the solid bounded by these. So if you let the integrand be 1 and you integrate over the solid, this equals the volume. So like if I'm in meters here, I need 144 cubic meters to fill that sucker up. Okay, we're going to do one more to set up. In this one, use a triple integral to find the volume of the solid bounded by the paraboloid x equals y squared plus z squared and the plane x equals 16. Okay, let's draw this. How does that paraboloid look? It's going along the x-axis. But we're cutting it off where? At x equals 16. So you have this face here, and that face right there that you cut it off has x equal to 16. And here is your paraboloid, x equals y squared plus z squared. You guys tell me, where's the base? The circle. Definitely the circle. Let's draw our base. Shall we draw our base? Let's draw our base. Our base, we wanted to draw our base. Our base, notice if x is 16, the equation for the base is y squared plus z squared equals, if x is 16 here, because you see all these points are on the paraboloid, but x is 16, equals 16. What's that? What is that? A circle. Circle of radius 4 is my base. You guys tell me, when we do our dy dz's, we're going to be using polars. So let's set up our volume. Setting up our volume here. We make it be a 1 because we want this integration to give us the volume of this solid, because then we're summing up our delta V's and we're just getting the volume of that lovely paraboloid that's been truncated by the plane, x equals 16. So if I take a point in the base, notice the base is in terms of x's and z, in terms of y's and z's, so we're going to be integrating with respect to x first. What is x ranging from? Now notice increasing x goes this way, so we're starting from a point on the paraboloid till we get to here. Here, x is y squared plus z squared, and then when we get here, x is 16. Okay, now you guys told me let's use polars. Instead of going dy dz for this, let's use polars. If we use polars, I'm going to let y be r cosine theta, z be r sine theta, and it used to be x squared plus y squared, so what? This is going to be y squared plus z squared is going to be r squared. So instead of putting in dy dz, we're going to go r dr d theta, right? And what's r ranging from? 0 to 4. This is why polars are wonderful when you have circles. You only use polars when you have circular regions. And my theta is going from 0 to 2 pi. But y squared plus z squared is r squared. You want me to do this? No? Okay. If you want me to do it, just email me and I'll write it out. This one, the answer turns out to be, after about 4 or 5 minutes of work, 128 pi. Okay, we only have one more section to do. I want you to, now notice we skipped a couple sections. It's not a physics class, and so I skipped that one section that has center of mass and that type of stuff. So instead, I want you to read pages, look over the examples, 1059 through example 4. You don't have to read beyond that. And then on pages 1066 to 1067, I like 3 through 19, the odds. And as always, if you're struggling a little bit, sometimes you need somebody just sitting with you one-on-one going over some of this stuff, please email me or drop by my office or leave voicemail, and we'll work on it together. Okay, see you next time.